Hi guys, this is Andrew. I'm one of the practicum students that is working with your class this semester. Today I'll be going over one of your week 8 materials in the Infinite Arithmetic series. This video will be going over some notes about how to do those problems and about what the Infinite Arithmetic series is, as well as talking about a few example problems and then taking a look at what your homework problems will be for this unit. So first off, we'll talk about a few of our objectives. The first objective is to define what an infinite arithmetic series is. And how that would differ from arithmetic series and arithmetic sequences, both in the finite and infinite senses. And then we will also determine if an infinite arithmetic series converges or diverges. With that, we're going to discover a general rule for the convergence and divergence of such series. So the first thing to do, we'll go over a little bit of a review of what the arithmetic sequences and series are. So an arithmetic sequence is a sequence of numbers where the consecutive numbers, also known as terms, have a constant difference, which we will also call the common difference, and is denoted by the letter D. So these sequences and eventually will be series typically have a pretty constant flow to them. They almost look like a linear function. They have something being added or subtracted to them every single time. If we look down at the bottom left, we will actually see an example of a arithmetic sequence. We have the sequence 1, 3, 5, 7, 9, which is the odd numbers, and this continues on. Each time we're adding plus 2, we have 1 plus 2 equals 3, and then 3 plus 2 equals 5, and then 5 plus 2 equals 7, and so on and so forth. So that is what a arithmetic sequence is. And then the second thing to talk about is an arithmetic series is the summation of all the terms in an arithmetic sequence from a sub 1 being the first term to a sub n being whatever nth term. If the series is finite, then the formula below applies. So the formula we're talking about for that is actually this right formula, but to quickly touch on what this left formula is addressing, this is how we find a sub n in a typical series. So in this first one, for example, we would have that a sub n, if you're trying to find this fourth term right here, which is this 9, to find that we would have a sub 1, which is equal to 1, plus n, which is the fifth term right now, minus 1, times d, which is 2, so then we would have 1 plus 4 times 2, which is equal to 9. And then looking back on that right side again, we have this is the summation formula. This is just saying we're going to take all the terms that were found with this formula right here from the first term, which is n equals 1, up to the nth term, and then we're going to add them all together. So to look a little bit more at the infinite arithmetic series, it's similar to an arithmetic series, except for there's infinitely many terms in the summation of the sequence. We're not stopping at the nth term, we're not going to 10 terms, 20 terms, we're going to infinity. So a couple of examples below is we'll have our first series is S of n, which is the series we actually just looked at in the last slide. This time it'll be 1 plus 3 plus 5, so on and so forth, up to 11, and then continues after that. If we were then to take some partial sums, we will have that the first term is equal to just 1, the first and second term together is equal to 4, and then the first, second, and third terms is equal to 9, and so on and so forth to the sixth term, where we have this whole sequence of 6 added together to get us 36. And then additionally, a second one we can look at is R sub n, which is the summation of the following sequence: 5 plus 2 plus negative 1 plus negative 4 plus negative 7 plus negative 2 plus so on and so forth. So the partial sums there again are shown at the bottom down here. The one thing to note from these, if we look at a general trend, how are these numbers changing as we go on? We'll notice that from 1 to 4 it's increasing, and from 4 to 9 it's increasing, and then as a whole from 1 to 36 this whole series is increasing, and then the amount is increasing is changing a little more each time. It's becoming a little bit larger. And then the opposite is true for this one over here. If we look at the general format of how this is changing over time rather than just the first couple terms, we'll see that this series, these partial sums, is overall decreasing, with each consecutive decrease being larger and larger over time. So now if we take a look at some graphs of what that would look like, we'll see on the left here we have of S of n, which was our series of 1 plus 3 plus 5 plus 7 plus 9 and so on. So we see here the graph has a general upward curve, which supports the idea we talked about of how the series is increasing over time and how the series values from term to term, the increase there from partial sum to partial sum is ever increasing, versus R sub n, which actually goes up initially because of the values that are in it, but as a whole is still trending downwards, and the value between partial sum to partial sum is larger on higher values of n. So generalize the statement we just said. And before I actually say that real quick, we'll just address this. S of n has a positive common difference of plus 2, whereas R sub n's common difference is negative at negative 3. So there's a couple things to note as we kind of look at the general patterns of this. To generalize this, though, the positive common difference causes the partial sums to tend towards the larger positive values, while the negative common differences cause the partial sums to tend towards larger negative numbers. So to talk about our term, what we were trying to tending towards that we talked about in the last slide, we get to the idea of a limit, where a limit is the value that a function or sequence tends towards as the input value increases. So if we take that term, we go back one slide, that is saying that, so what value is, or what type of value is this sum tending towards as you increase as the input gets higher and higher? So it's saying like, okay, as we go from 1 to 2, and then 2 to 3, 3 to 4, and then maybe like 10 to 11, 20 to 30, etc., etc., is it increasing or decreasing? Is it getting closer and closer to a single number? What is it doing? And that will define what convergence and divergence is. So a limit is said to converge when the values, or output values, I should say, approach a fixed number. So this would be if the value curves into, for example, let's say, and converge to a value of 8. So all this values were all summed together and it converged to 8. That would be convergence. Otherwise, the limit is said to diverge if the values do not approach any fixed number. Divergent limits can approach any of the following, including going to positive infinity, negative infinity, or just not going to any value at all, such as if the series is bouncing back and forth between multiple numbers or is not precisely going towards positive or negative infinity, while not also going towards a single number. So to look back at these numbers, or these partial sums we already found, we'll find that S of n is tending towards larger positive values, so that we would say that this diverges to positive infinity, whereas R sub n is tending towards larger negative values, so we would say that diverges to negative infinity. Based on the fact that we already were given that these common differences, the positive common difference had to do with a positive infinity versus the negative difference had to do with a negative infinity divergence, it would appear that we can generalize this phenomenon based on the common differences. So to look at that, we have actually this general rule right here. The important parts to highlight of this are just that when d right here is greater than 0, then we have a positive infinity, and then if d is less than 0, we have a negative infinity. So just read those out real quick too, just so you get that vocalized in your head. If d, the common difference, is greater than 0, then the series diverges to positive infinity, whereas if the common difference d is less than 0, then the series diverges to negative infinity. So go into our first example here. Example 1 is talking about the divergence of infinite arithmetic series. So the problem descriptor as a whole is to determine whether the infinite arithmetic series diverges to positive or to negative infinity. So if we look at this problem, we have A says, what does an infinite arithmetic series with a common difference of plus 7 or positive 7 diverge to? So if you remember our rule was if d is greater than 0, which it is here, then we diverge to, and you guessed it right here, this part right here can go to right here to say positive infinity. And then the second question, well, actually, I'll press this for part first. So when you guys are doing this problem, this is kind of what we're looking for, kind of what I'm looking for in these problems. Write out the rule that applies to this part, and just make sure that you make some note of it's plus 7 is our common difference. You could just write maybe like d is equal to plus 7, so then it goes to this with like an arrow maybe. Although this part right here is fine where you say if d is greater than 0, then put it there, it diverges to positive infinity. And then the second question here, part B, is kind of the opposite. What does an infinite arithmetic series with a common difference of -5 diverge to? So we would actually just write the opposite of the previous rule, where it'd be if d is less than 0, then the series diverges to negative infinity. So again, you kind of just look at the common difference value. Again, we're given that right here as a -5, so d is equal to -5. We then write out the rule if d is less than 0, then the series diverges. Write that e properly. And my r as well, those are really bad. It diverges to negative infinity. So just remember here, if the common difference is positive, then it goes to positive infinity. If the common difference is negative, then it goes to negative infinity. And then just look at a couple of the homework problems you guys have. These are actually the only 3 you have on this part of the problem. In order, they are asking what happens if it is -4, +8, and plus 0.5 for the common difference. And then again, you guys just want to write out similar to this, write out the rule if it is d is greater than 0, or if d is less than 0, then the series goes to whatever value. Those problems are pretty simple. Just you can literally just write out the rule again. So if ... and then write out what happens. So we'll move on to a second type of problem that's a little bit more involved. These problems are finding the divergence of the series again. However, this time you're not given the common difference. So this time we have to find the common difference and determine whether the infinite series diverges to positive or negative infinity. So the first problem here, we have the series -3 plus 1 plus 5 plus 9 plus, and it continues. So what we'll first have to do is we'll have to find some common differences. So if we look at this right here, we would have 1 minus -3, which is equal to 4. And then we would have 5 minus 1, which is equal to 4. And then again, we would have 9 minus 5, which is equal to 4. So we found that we have a common difference of d is equal to 4. So then again, all we have to do right here is we're going to write out if d is greater than 0, then it diverges to positive infinity. So again, you guys, all you have to do here for work-wise, you guys want to show just what the common difference is, and then write it as d right here, and then write that the this part right here diverges to positive infinity. The rule part does help you write that out, and that'll be included on the worksheet. So B of this problem is a slightly different one. Again, we'll have to find the common differences and then determine if it goes to positive infinity or negative infinity. So let's again do that what we just did. So we have 5 minus 11 for our first difference, which is equal to -6. We then have -1 minus 5, which is equal to -6 again. And then our final one is -7 minus -1, which is equal to, this becomes a big plus right here. So we have -7 plus 1, which is -6. So again, now we found that d is equal to -6. So then the series, so I'll just circle here, the series diverges to, actually we will erase that, or it's a little better for you. So the series diverges to, we'll just circle it right here, to cross out, the series diverges to negative infinity because our d value is negative. So the third one here, again, goal is again just to find the common difference and then determine if the series diverges to positive or negative infinity. So the first difference would be 5 minus 2, which is equal to 3. We would then have 9 minus 5, which is equal to 4. And then we would have 14 is minus 9, which is equal to 5. So if we notice here, we have 3, and if we notice here, let me not do it that way, we'll do this way. 3 does not equal 4, and 4 does not equal 5, nor does 3 equal 5. So what we've just discovered is that this actually doesn't have a common difference. So in this case, this rule we have right here is actually only valid if we have a series that has a, if the series itself is arithmetic. It is not implied here at all that this is arithmetic. It's just an infinite series. So in this case, we're going to cross this out, and then we're going to write not arithmetic. So unknown. That's all we have to write there. You guys are basically determining if it is arithmetic, like you've done before. So in this case, since it is not arithmetic, you actually don't have to do anything with it. And in this case, we can just leave it as is. You guys can write something in nature of no common difference, and then so not arithmetic, and we do not know whether it diverges to positive or negative infinity. The level that you write for that doesn't necessarily matter, but we do want to for sure see this work right here that talks about what the common differences is. Okay, and then we move on to some related homework problems for you guys. So the related homework problems have the same problem right here as before. So just make sure you guys do these problems the same way as you did before. Again, we want you guys to use the common difference right here to then imply whether it diverges to positive infinity, negative infinity, or if it, like the last problem, like part C, is not arithmetic at all. The hint here is that there is one of these that goes to positive infinity, one that goes to negative infinity, and then one of them is not arithmetic at all. So just know that you're going to use one of these each. The order I will not tell you at this point. You guys will have to do that on the actual assignment. So yeah. And then you guys, just to wrap it up and to talk about a little bit what you guys have to do for reminders, remember to use this video along with help to complete the infinite arithmetic series and other series assignment from this week's folder. There is actually another video that will be coming that'll be right after this one about the other series as notes, and again help for that. You'll need both of those to actually do the assignment for that. And then additionally, make sure you guys do the geometric sequences and series stuff, as well as the infinite geometric series material that are also in this week's folder, and all that as preparation for a test that you guys will be doing at the end of the week.